Welcome to lesson 2-5, Compare and Order Real Numbers. By the end of this lesson, hopefully you can say, I can use rational approximations or fractions to compare and order real numbers, including irrational numbers. So fractions or decimals, it doesn't matter as long as it's rational approximations, so estimations. So we're using fractions and decimals to estimate. So let's look at this. You can compare and order real numbers by writing them in the same form, meaning as all decimals or as all fractions. One way to do this is to use or approximate the decimal expansion of each number in order to compare or order a set of numbers. Complete the following to compare and order the set of numbers shown. So the idea is we're going to write each number in decimal notation. So in your calculator, you'll write 18 divided by 5. You should get about 3.6. Pi is about 3.14. And then the square root of 11 is about 3.32. So notice how this is equivalent and these are approximations. So pi and the square root of 11 are irrational numbers. So these are irrational. That means they're going to have decimal expansions that go on into infinity and they don't stop. But as you can tell, 18 over 5 is equivalent to 3.6. So now we're going to compare each set of numbers using less than, greater than, or equal to. So this one is less than. This one is greater than. Right? All right, so when we put these in order, notice how we have 3.14, 3.32, and 3.6. And so 3.14 is less than 3.32, which is less than 3.6. And so we're going to write their equivalents down. So now that tells us pi is less than the square root of 11, which is less than 8 divided by 5. When we graph it on a number line, we use our decimals to help us. So pi is between 3.1 and 3.2. Square root 11 is between 3.3 and 3.4. If we wanted to write our decimal expansions above, we have 3.14. Square root of 11 is about 3.32. And then 18 divided by 5 is 3.6. So it's exactly on the 3.6. When we order them from least to greatest, if you wrote them like this, it's just going to be pi square root 11 and then our 18 divided by 5. Go ahead and let's move on to example 1. So we're going to use which symbol less than, greater than, or equal to would complete the statement square root 8 blank 2 and 2/3 to make a true statement. Then graph the numbers on a number line. So first we're going to find our decimal equivalents. So when we plug in the square root of 8 into our calculator, we should get about 2.8. For the next one, we're going to get about 2 and then when we plug in 2/3 into our calculator, we should get about 0.6, and it looks like it's repeating. So we can use bar notation to show that 6 is repeating. Notice how we found an equivalent versus an approximation. So now we know that 2.8 is greater than 2.6 repeating. So we know that the square root of 8 is greater than 2 and 2/3. When we graph it on a number line, we're going to graph it where we have 2 and 2/3 between 2.6 and 2.7. And then we have 2.8 and 2.9, and that's where we're going to graph our square root 8. Let's look at our first check. Go ahead and try this out. Which symbol, less than, greater than, or equal to, would complete the statement square root of 25 over 2 something over, or compare it to the square root of 6.25 to make a true statement? Then graph. So first we need to compare them. When we do this, we have to do square root 25 over 2, which is actually 5 over 2, which gives us 1 2 1/2, which tells us this is 2.5. Now let's do the square root of 25. So I actually have to put this into my calculator. So I'm going to pull up my calculator and I'm going to do the square root. So let's see, square root of 6.25, and I'm going to get 2.5. Those look like they're equal to each other. Let me check the answer. Yep, they're equal to each other. So even though they don't look like they'd be equal to each other, they are. So let's try this next one. Now we have to graph them correctly. So they should be graphed in the same spot of 2.5. So it looks like B should be our answer. And it is. Next example. So again, we're going to plug the square root of 6 into our calculator. Don't forget it's negative. So we're going to have negative 2.4. And now we have pi divided by 2. And it's a negative. So we're going to have a negative, and then whatever 3.14 divided by 2, which is 1.57. And we always want to round to the nearest tenth or the hundredth. When we're looking at decimal approximations, we really could have rounded this to negative 1.6. So the only time this would be an issue is if we had the same number for 1 and the same number for our tenths place. Then we might want to round it to our hundredths. But I would round this one to 1.6. So when we compare them, we know that the square root of 6, which is our negative 2.4, is going to be less than our negative 1.6, right? And we're going to graph those on a number line. Now, how does graphing numbers on a number line help you know whether to use less than, greater than, or equal to when comparing them? So think about graphing it on a number line. If we graphed these on a number line before we said which one was bigger, we would know that negative 2.5, negative 2.4, and then we're going to go all the way up to negative 1.6 and negative 1.5. Because we knew where they fell on the number line, we would understand that negative 6, square root 6, and negative pi halves, we would see where they fall on that number line, and then we would know to put the less than symbol in there. All right, go ahead and check. So when we plug in negative square root 5 into our calculator, what do we get? Let's see. Square root 5 into our calculator, we get about negative 2.2, that's what we get. Then if we did 210 as a percent, we know we're going to take our decimal and move it over twice, so we're going to get negative 2.1. So that tells us that we're going to have a less than symbol, because negative 2.2 is less than negative 2.1. And when we graph it, we're going to have the square root of 5 between negative 2.3 and negative 2.2. Just be careful. And then negative 2.1 is going to be directly on the line. So it couldn't have been this one. It couldn't have been this one. And we knew that we had a little bit more than 2.2. So we knew it was going to be just above it when we had plugged it into our calculator, because technically this is 2.3, and then there was a lot of decimals after that. All right, example number 3. Order the set. So we're going to have squiggly brackets when we talk about something called a set. A set is just a list of numbers. So a set is a list of numbers, and that's usually going to be surrounded by curly brackets. So like 1, 2, 3, ... right? It's a list of numbers. So we're going to take these and we're going to order them from least to greatest. First thing we need to do is approximate the decimal expansion. We're going to approximate the decimal expansion. So when we plug the square root 30 into our calculator, we're going to get about 5.5. 6, of course, is 6.00 because we want to write it as a decimal. 5 and 4/5, plug in 4/5 into our calculator, we get 0.8, so it's 5.8. Then we can simplify 5.36 to about 5.37. We could have rounded this up to 5.4. That would be okay with the numbers we're working with here. And we're going to order them from least to greatest, meaning the smallest to our largest, right? So least to greatest. So what's the smallest one we have? It's going to be 5.36 repeating, or 5.37. Then we're going to have 5.5, then 5.8, and then 6. So to order these from least to greatest, we're going to have 5.36 repeating, square root 30, 5 and 4/5, and then 6. When we graph it on a number line, it's going to look like this. And of course, we're just placing it in between the numbers that our decimals showed us. How are comparing real numbers and ordering real numbers related to each other? Think about that. How are they related? Comparing and ordering. In order to compare, we have to order them because we're comparing their values. And so whenever we order them on a number line, that's how we can compare their values, because we know if we go to the right, we're going to go up or positive, and if we go to the left, it's going to be a negative. And then we can see where they fall on the number line, and that's going to tell us which ones are greater and which ones are not. Look, I made a face. All right, let's go to the next check. So we're going to order these sets of numbers. So we have the square root of 3. We need to figure out what that approximation is. We have pi over 2. We already figured out that approximation. We have 1.6%. We need to figure out that approximation. And then 1.35. So first thing we need to do is figure out what those equal. Go ahead and try that right now. 1.73 for the square root 3. Pi over 2. What did we have for that one? Why would we do extra work if we already did it? So 1.57. Okay, 1.57. Decimal for a percent, we're going to go out 1, 2. So we have 0.016. And then 1.35, where this is repeating. Oh, that's weird. I don't think they meant to put a decimal there, because look at how their answers look right here. There's a typo. Oh no. So let's see what it is with the typo, and then let's see what it is without the typo. So this one's a typo. I think they meant to say 160% so that they could get 1.6 as their decimal approximation. That's so funny. Okay, so now we have 1.35 repeating, so we're going to get 1.36. So now when we order these, what's our smallest? Technically, this one would be our smallest. So we can't even use the typo to get our answer from our options. So that tells us we have 1.6. So technically 1.35, so that eliminates the last one. Next from 1.35 is going to be 1.57. So it's going to be A. So let's check our answer. And we get A as our answer. And be careful of typos. So when we plot this, that tells us we're going to have 1.35, then pi over 2, then 160%, then square root 3. So it looks like they put them in the correct order. So now let's see. 1.5 repeating is just a little bit more than 1.35. So that tells us that eliminates the one down here, and it eliminates the one down here, and we'll double check. Yep. So that eliminated C and D because it's going to be just a little bit more. It's not exactly 1.35. And then pi over 2 is 1.57, not 1.55. So it should be A. Next example, it says on Wednesday, there are 83 and 1/3% chance of rain. On Thursday, there is 9/10 chance of rain. On Friday, there is 6 out of 7, which we write as 6/7 chance of that it will rain. So on which day is the greatest chance of rain? So we're going to do comparison using decimals. So when we plug this in, we're going to get 0.83. Plug this into our calculator, we get 0.9. Plug this into the calculator, we get 0.86. So that tells us we're going to do 0.9 is greater than 0.86, which is greater than 0.83. And so that tells us that 9/10 is greater than 6/7, which is greater than 83 and 1/3, meaning 9/10 is our greatest chance of rain, and that was on Thursday. Go ahead and try the check. The table shows the on-base statistics for 3 players at a recent baseball tournament. Which player had the greatest on-base statistic? So we have 15 out of 21, 14 out of 19, and 72.5%. So let's see what these equal. So if we plug them into our calculator, what do we get? So for this one, we're going to move our decimal over twice. We get 0.725. 14/19. When we plug that into our calculator, we get 0.736. So I'm going to write that down, 0.736. And now we get 15 out of 21, 0.714. Let me make sure I did 14/19 correctly. All right, I did. All right. So when we compare these, which player had the greatest on-base statistics? So when we compare this, we're going to have player 1 is less than player 3, which is less than player 2. And so player 2 should be our greatest on-base statistic. One way to look at these is to line them up. So if we had 0.714, 0.736, and then 0.725. So 7's the same. So then next we want to look at our hundredths place. So that tells us player 1 is our least, player 2 or 3 is our next, and then our greatest is player 2. So that should be our answer, player 2. And we're going to do the apply together in class. I have also assigned the online assignment to help you with this.